Welcome to the fastest way to master data structures and algorithms. Today we are solving LeetCode 98, Validate Binary Search Tree. This problem is asked in top tech companies like Google, Amazon, and Microsoft. Let us master it. Let us look at the problem statement. We are given the root of a binary tree. Our goal is to determine if it is a valid binary search tree. A valid BST has three rules. First, every node in the left subtree must be strictly less than the current node. Second, every node in the right subtree must be strictly greater than the current node. And third, both left and right subtrees must also be valid BSTs. If all three rules hold, we return true. Otherwise, we return false. For example, consider the tree with root 5, left child 1, and right child 4, where 4 has children 3 and 6. Is this a valid BST? No. Because 4 is in the right subtree of 5, but 4 is less than 5. So it is invalid. Now, let us think of the perfect analogy. Imagine you are a customs officer at a very strict checkpoint. Every passenger passing through your lane must carry a number that is strictly between the minimum and maximum allowed values for that lane. When a passenger moves left, you lower the maximum. When they move right, you raise the minimum. If at any point a passenger's number violates the range, they are rejected immediately. This is exactly how we validate a BST, by passing down valid min and max boundaries at every single node. For our strategy, we use a recursive approach with min-max bounds. At each node, we check if the node's value is strictly greater than the lower bound called min, and strictly less than the upper bound called max. We start with min as -infinity and max as +infinity at the root. When we go left, max becomes the current node's value. When we go right, min becomes the current node's value. If any node violates its bounds, we return false immediately. This is O of n time and O of h space, where h is the height of the tree. Now let us dive into the dry run. Our tree has root 5 at the top. Left child 1, and right child 4. 4's left child is 3, and 4's right child is 6. We start at node 5. Bounds, min is -infinity, max is +infinity. 5 is in range. Valid. We recurse both ways. We go left to node 1. Now bounds become min -infinity and max 5. Is 1 in range? Yes. 1 is greater than -infinity and less than 5. 1 has no children. This branch is valid. Now we come back and go right to node 4. Bounds, min is 5 and max is +infinity. The critical question, is 4 strictly greater than 5? No. 4 is less than 5. 4 violates the minimum bound. We immediately return false. The tree is not a valid BST. The answer is false. Now let us look at the Python code. We define a helper function called validate that takes a node, a minute value, and a max value. First, if the node is none, we return true, because an empty tree is always valid. Then we check if node.val is less than or equal to min.val, or if node.val is greater than or equal to max.val, we return false immediately. Finally, we recursively validate the left subtree passing min.val and node.val as bounds. And we validate the right subtree passing node.val and max.val as bounds. We return true only if both subtrees pass. The main function calls validate with root, -infinity, and +infinity. Looking at the complexity. The time complexity is O of n, because we visit every single node exactly once. The space complexity is O of h, where h is the height of the tree. In the worst case of a skewed tree, this becomes O of n. In a balanced tree, it is O of log n. And that is validate binary search tree, mastered. The key insight is that a BST is not just about local comparisons. Every node must satisfy the global min and max constraints inherited from all of its ancestors. Save this video for your next coding interview.